Welcome to Module 2, where we bring the science of well logging to life through interpretation. This is where data becomes decisions, where the lines on a log transform into a clear picture of what lies beneath. In this module, we will cover lithology identification, porosity determination, fluid saturation analysis, Shelly sand interpretation, advanced logging methods, and practical applications in reservoir characterization. 1. Introduction to log interpretation. Log interpretation is the process of analyzing and combining various well log measurements to deduce the lithology, porosity, fluid content, and other properties of the subsurface formations. The interpretation process often involves cross-referencing multiple logs, integrating core and seismic data, and applying geological knowledge to ensure accuracy. 2. Lithology identification. Lithology refers to the physical characteristics of the rock, such as composition, grain size, and texture. Well logs provide indirect indicators of lithology. Gamma-ray logs measure shale content. High readings typically indicate shales, while low readings indicate cleaner sands or carbonates. Density neutron crossplots can help differentiate between limestone, dolomite, and sandstone. By combining these logs with resistivity and sonic data, geoscientists can build a reliable lithological profile. 3. Porosity determination. Porosity is a critical property because it tells us the proportion of void space in a rock, which may be filled with fluids. We can estimate porosity from density logs, by comparing measured density to the density of the rock matrix. Neutron porosity logs, which are sensitive to hydrogen content. Sonic logs, by relating travel time to porosity. Using more than one method helps compensate for the limitations of each and improves accuracy. 4. Fluid saturation and hydrocarbon detection. Fluid saturation tells us what fraction of the pore space is filled with water, oil, or gas. Resistivity logs are particularly useful for detecting hydrocarbons because oil and gas have much higher resistivity than salt water. Hydrocarbon-bearing zones often appear as high resistivity intervals on a log, especially when combined with low gamma-ray readings and good porosity indicators. 5. Permeability indicators. Permeability measures the ability of a rock to transmit fluids. While it is difficult to measure directly from logs, we can infer it from porosity, lithology, and empirical correlations. In some cases, advanced tools like NMR logs provide more direct estimates of permeability. 6. Shelly sand interpretation. Shales complicate interpretation because they contain bound water that affects resistivity and neutron measurements. Correcting for shale effects is essential in clastic reservoirs to avoid underestimating hydrocarbon saturation. 7. Advanced logging methods. Modern logging offers advanced capabilities. Nuclear magnetic resonance (NMR) logging provides direct measurements of pore size distribution and fluid types. Borehole imaging tools produce detailed images of the borehole wall for structural analysis. Spectral gamma-ray logging differentiates between types of clay minerals, improving lithology identification. 8. Applications in reservoir characterization. Well logs are indispensable in defining net pay zones, estimating reserves, mapping facies, and assessing reservoir quality. When integrated with seismic and core data, they provide a three-dimensional understanding of the reservoir. 9. Integration with other data. Effective reservoir evaluation requires combining log data with core data for calibration, seismic data for spatial context, production data for validating interpretations. 10. Case studies and practical examples. In real-world cases, log interpretation has helped identify bypass pay zones, optimize completion strategies, and avoid costly drilling mistakes. Understanding the full potential of well logs is not just about reading curves, it's about seeing the reservoir in your mind before it's ever touched by production equipment.